I want to start today by, I'll introduce Tiffany Kapler. She's a public outreach specialist for NASA's Lucy mission. She grew her career in science communication as an environmental education Peace Corps volunteer in Bolivia, and then as an educator at the Denver Museum of Nature and Science. She's developed formal and informal education engagement programming for several different organizations. Tiffany is passionate about sparking curiosity in learners of all ages as they explore and learn about the world. And our subject matter expert today for Lucy is Dr. Keith Knoll. He's the project scientist for the Lucy mission. And Dr. Knoll studies asteroids in the solar system using instruments like the Hubble Space Telescope, the Keck Telescope, and the recently launched, and personally what I'm excited about, the James Webb Space Telescope. He's been at NASA Goddard Space Flight Center since 2011, and before that, he was with the Space Telescope Science Institute out of Baltimore, Maryland. He's got a BS in physics, an MS in physics, and a PhD in planetary science, and we're just thrilled to have Dr. Knoll with us today. And at this time, I'm going to turn this over to Dr. Knoll, and we'll go from there. Thanks so much.
Thank you, Barbie. So I'm really delighted to be here. And I'm going to try not to go slow on my first slides because I usually do that and I don't want to run out of time. But I thought I'd share with you a photo. I'll come back to this at the end too, that all of these missions really involve, lots and lots of people. This is our science team at the launch, the day before launch in Florida just a year ago. But there's many, many more people. And I think that's of the messages you can bring back to your students. The different ways to participate are nearly endless, and you don't have to be something that you might think is, out of your personal reach. First of all, it's probably not, but also there's many different ways to do it. So that's really important message. And let's talk a little bit about Lucy. So unlike most NASA missions, Lucy is named, it's not an acronym, it's named after the Lucy fossil that was found in Ethiopia in 1974, and the fossil itself was named after the Beatles song that they were playing in the camp in the Afar region of Ethiopia when they found it. So there's a connection to the song, the Beatles song, Lucy in the Sky with Diamonds. So we've taken our inspiration for our patch, both from the fossil and from the song. But the reason that we chose fossils as an inspiration is that we think of these objects, these Trojan asteroids, and I'll explain what they are in a minute, as samples of what was the most common type of planet-building object in the solar system 4.5 billion years ago. We tend to call those planetesimals, and these were orbiting at the edge of the disk that the planets formed from. And because of the chaotic dynamics that take place at the very early stages of our solar system, these are preserved in this relatively easy to get to place, which we call the Jupiter Trojan. So, and we don't know every part of that story that I just told you. So the real reason we're going is to test that and to figure out if we really do understand these ideas about how the early solar system forms and evolves. And I think that's also one of the more exciting things about our mission, is that it really is giving us the opportunity to do science in a way we don't always get to do in planetary science, where we're going to be able to compare many different objects and really do the gold standard of science, the way you want to do it. So this is a view of our solar system that we don't often show to students. This is looking sort of in a zoomed out view. So the purple circle there is Neptune's orbit. Jupiter's orbit is the one with the arrow pointing to it at the inside, and you can't even see the Earth's orbit in the very middle there. But all the little tan dots are all the asteroidal bodies. We tend to call them small bodies. So that covers comets as well as asteroid type objects and everything in between. And since the early 1990s, we've discovered this entire new belt of objects orbiting outside of Neptune. That's what we call the Kuiper belt. But we've also continued to discover, millions more objects in the main asteroid belt. And the main asteroid belt itself is more complicated than a single belt. And so if we zoom in the next slide, now we're looking, Jupiter's orbit is this outer circle. We can't even see Saturn, Uranus, and Neptune. They're out beyond the slide here. But this is the way we usually show the solar system with the orbits of the planets. And sometimes you would see, and Barbie, if I could grab the pointer, okay. Sometimes on those maps, you'll see this space between Mars and Jupiter filled with the asteroid belt. But there's parts of it that extend further out. And in particular, these two clumps of light green are what we call the Jupiter Trojans. They're in a very special spot where the Jupiter's gravity and the sun's gravity balance in such a way that objects that get trapped there tend to remain there. And so these objects have been there stable for the entire length of the solar system in its current configuration. We launched last year, October 16th. We have a main belt asteroid rehearsal in 2025. And we're going to a total now of 8 Trojans because we've found 2 satellites since we started planning this mission. Okay, there's a little movie here that I'm going to ask Barbie to run, but this shows you this idea of this early chaotic phase of the outer solar system. What we've figured out is that the planets formed in a much more compact figuration than we see them now. So you see in this figure here, you have Uranus and Neptune much closer in, and then a disk of smaller planetesimals exterior to that. And then at some point, from gravitational resonances, I'm going to run this again, the giant planets start moving around. And in particular, Uranus and Neptune move out into that disk. They scatter it. Most of the material is lost. Some of it is trapped in stable orbits just outside of Neptune, and that's what we see now as the Kuiper belt. But another branch of those scattered objects is trapped in these Trojan orbits near Jupiter. And so that gives us a convenient way of looking at objects that were originally out here in this very cold part of the solar system's disk where all of the material would be preserved because even things that are normally gases are frozen as solids. And then instead of being pushed out to 30 or 40 astronomical units very far from the sun, they're here at only 5 astronomical units, which we could actually get to with a spacecraft like Lucy. So that's how we ended up with this mission. It's a great way to test these ideas about what was going on in this chaotic phase of the early solar system. And here's a diagram that we call the pretzel diagram, and it's a very complicated looking thing. It shows you the trajectory of Lucy in the green, and we start out launching from the Earth. We go around a couple of times. We loop out into the leading cloud of Trojans, which are called the L4 Trojans. And then we come back for another pass by the Earth, and then back out to the L5 Trojans. This is in a special frame that's fixed relative to Jupiter. So it's a little bit tricky. And in the next one, I'm going to show you, I'm going to ask Barbie to run another movie for us in a sort of a normal frame, in a fixed frame, an inertial frame, what Lucy's doing. So here we go. It's launched 1 year orbit, and that's where we are right now. Another longer loop going out, comes back for another close pass by the Earth, and we gain some more energy, and we loop out, and we throw ourselves up in front of these Trojans, and we have this encounter. These are the 4 objects in the larger bright white there are the objects that we're going to come close to. Then we fall back in. have another close encounter with Earth that just changes the direction a little bit. And then we have our last encounter in 2033 in March. And then we fall back in, and we keep falling back and forth between roughly the distance of Earth and roughly the distance of Jupiter for possibly as long as a couple million years. But that's how we carry out this mission. Okay, let's go back to our main slides. So as we've talked about in the movies you were seeing before, and as Tiffany's going to talk about some more, we're about to come up on that 1-year anniversary of launch when we have our first Earth gravity assist. These gravity assists, you can think of it as a way to sort of slingshot or gain some energy from the Earth. So Lucy steals a little bit of energy from the Earth, but it is completely negligible as far as the Earth is concerned. But it helps speed up and give energy to Lucy. And that's important because spacecraft like this are small. We really have to be very careful about our mass and conserve our fuel. So these boosts are essential parts of these mission designs. We'll do another one 2 years from now, and that's the one that will finally give us enough energy to get all the way out to the Trojans. And as you can see from this diagram, we're actually coming in quite low. So it's another moment of biting our nails, just like we were a year ago on launch. Now we're going to fly through this region that's crowded with satellites and debris. We have close communication with the folks that monitor that stuff. We have plans to do short diversion maneuvers if we have to. So far, it's looking good. So fingers crossed, we have a clean Earth gravity assist. So here's a cartoon version of the targets that we're going to see when we get to the Trojans. And the first thing you'll notice is that there's a big range in size. So almost a factor of 100 from the smallest satellite of Euripides, which is named Keta, up to the 2 components of the Patroclus-Menetius binary. You also see that we've tinted these slightly different shades of pink or gray, and that's to represent what we know about the composition of these objects from observations we can take from Earth, which is that they differ slightly. So these objects are all relatively featureless in terms of spectroscopy and spectral features. So that means that they reflect light at about the same intensity at all wavelengths, except some of them are a little more reflective in the red than the others. And that's a clue to composition, but we're not quite sure what to make of that. And part of the way that we're going to try to get the answers to that is by going and looking and seeing, is this a checkerboard with just bigger areas of very red stuff, or do we see very distinct differences? We'll also be able to measure the spectra, compare the spectra of specific regions, like craters, fresh craters, old craters, other kinds of terrain. These are all going to be ingredients into what we will eventually, throw together and sort out, and then try to come up with a consistent interpretation for what's causing these differences in these appearances. So talk about a couple of the objects. One of the first one that we get to is this object called Euripides, and it's a very special object in the Trojans. It's the largest remnant of a disruptive collisional family in the Trojans. And we've never visited an object like that with spacecraft before. There are other collisional families in the main asteroid belt. This is the only large one that we know of in the Trojans. But going there may tell us, first of all, just about these kinds of collisions in general. Collisions are a very general process that shape the asteroids and the Earth and other planets. And so understanding more about that by visiting a survivor, a remnant of one of these giant collisions, is going to be important. But the other thing might help us do is solve this mystery of why Euripides is less red than most of the other Trojans. And it's possible that is also connected to collisions. So you can imagine if what makes these objects red is a thin layer of material that's been sunburnt, so to speak, on the surface, and then it gets blasted away. That might result in a more neutrally colored object at the end of that. So those are the kinds of questions that we want to try to answer by going to this particular target. So let's go back to our main slides. But as I mentioned before, one of the strengths of this mission is if we only went to Euripides, we wouldn't necessarily know how to interpret that. But by going to more than one, and in particular, Orus is about the same size, but it's a much redder object. And that's a good science experiment now. So the only variable is the color and the collision, and now we have a test. The other thing I wanted to bring up is this link between the objects that got scattered out into the Kuiper Belt and then the objects that got scattered into the Trojans. One of the things that we see when we look at the Kuiper Belt are lots of binaries, and by that I mean things that have satellites that are almost the same size as the thing that's orbiting. So they're essentially orbiting each other, and it looks like from the frequency of these objects that we see there that these are fairly fundamental processes in the solar system. And so that's a very strong clue to, these things form this way. And stars also frequently form as binaries. And this may be a product of gravitational collapse. In the Trojans, we also see a few, not as many as in the Kuiper Belt, but a few of these equal mass binaries, and we're going to visit one. And so by comparing that to what we've already seen in the Kuiper Belt with the New Horizons spacecraft, it's going to give us a really good way to tie together these very distant but possibly related families of objects. I mentioned that we found 2 new objects. So here's an image at the top showing the Hubble Space Telescope. We did a very deep search of all of their targets, and around Euripides we found this one small object. We've gotten enough repeat observations that we actually know its orbit pretty well now. We know where it's going to be roughly when Lucy flies by. We're going to come very close to it. In fact, we may come closer to this satellite Keta than we do to any of our other Trojan targets. Unfortunately, that's not going to be necessarily helpful because the angles that are involved mean that we might have to turn our cameras completely backwards, which is something we can't do. We'll definitely get observations of it, but they may not be super close-ups. We also more recently found another satellite around one of our smaller targets, Polymele, and we don't have an orbit for this. We've only seen it once. We got extremely lucky in one of our ground-based stellar occultation campaigns that the light from the star that we were monitoring blinks out as the Trojan asteroid passes in front of it. And we put some extra telescopes on either edge just in case we're off a little bit. 2 of those extra telescopes on the edge saw the light of the star blink out, but at a different time. And it shows that there's a smaller object orbiting possibly 250 kilometers away from the primary. So that's quite exciting. I think we're going to want to try to follow up before we get there. Certainly, we'll definitely see it with Lucy when we get there.
Dr. Knoll, there's been asked for a clarification about the satellite and by what you mean by satellite in terms of, I think the difference in, actually, we had someone actually help us in the chat in terms of defining what a satellite is and what you're talking about. They're actually natural satellites you're seeing, not so much man-made. So would you care to clarify that whenever you say satellites and rings?
Yeah, those are natural satellites that we're talking about. So, and, we could go down a rabbit hole in terminology. Binaries are also often called satellites. The difference being that in those cases, the 2 components orbiting each other are very nearly the same size. That's not something we see so much, although Pluto and Charon orbit a point in space between them. Their barycenter is not inside Pluto, so many people would call that a binary. And the Earth and Moon will eventually be a binary system. It isn't yet, but the Moon's receding from the Earth. And at some point, the barycenter of the Earth-Moon orbit will be outside the surface of the Earth. So anyway, that's just sort of a fun aside. Don't get me going. We'll use up the rest of the time. But yeah, these are all natural satellites. Nothing from Earth has ever visited any of these objects. Oh, and just a word about rings. We do know that several asteroids are known to have rings. These are presumably from collisions or satellites that have been broken apart. The ring formation process is not completely understood, even for things like Saturn and the other giant planets. It was a big surprise that some things as small as asteroids could even have rings. But since we now know they exist around at least some asteroids, we're going to look for them. They would be much closer in than anything we can see from the Earth. So those are things that we will only have a chance to see when we get there with Lucy. Another interesting aside, Quetta is named for Enriqueta Basilio, who was the first woman ever to light the Olympic torch. We selected that because it is related to the name of Euripides itself. But this was the first Trojan to be named for Olympic athletes, mainly because the tradition up until recently has been that they would name from characters from Homer's account of the Trojan War. And even though he's very long-winded and names lots of people that die in the battles, it's not an unlimited number. And we now have many more Trojan asteroids than names in the Iliad. So we adopted this convention of using Olympic athletes. It allows us to be much more diverse in the nomenclature. We can pick people from different countries, women as well as men. We've named some for para-Olympic athletes, but the first one was Enriqueta Basilio, and we were very delighted to be able to host her adult children and grandchildren at our launch last year. Okay, so here's how we got Lucy to where it is. We packed it up in this big box that you see on the left, loaded it onto that big airplane that you see at the end of July last year. We flew it to Cape Canaveral, where it was unloaded right before a giant thunderstorm hit. A few weeks later, it gets encapsulated in the capsule that you see on the right and hoisted on a big crane on the top of the rocket that you saw in that picture that I showed at the beginning. Here's the breakdown of what the rocket looks like. We launched on an Atlas 5401. It's almost 200 feet tall, and we got a fantastic launch that has helped us immensely because we didn't have to do any early trajectory corrections, and that saved us fuel, and it saved us some headaches in terms of the situation that we've had with our solar array. We are carrying an instrument package on a pointing platform. We have the LORRI, that's our long-range camera, so that's like your telephoto lens. Then we have TT cam, that's our tracking camera, so that's our wide view and wide angle lens. We use that mostly for navigation, but when we get very close, we'll also use it for some science. Then we have our thermometer, that's LTES. That's going to take the temperatures of the night side and the day side, and the difference between those and how rapidly they change is going to tell us something about the surface material. LRALPH is our 2 instruments for the price of 1. It's got a visible color camera, and then it has an infrared spectrometer. And I know I've said spectrometer a few times. That is when you take light, spread it out like with something. A prism is one way to do that, and you're measuring the intensity of the different colors at each wavelength. And that tells you a lot about compositions. That's our main way of understanding the composition of surfaces. We also have a big radio antenna. It's about 6 feet, 2 meters in diameter. We use that for communication, but we can also use that for science because the frequency will change just a little bit. By careful Doppler measurements, we'll be able to see how we accelerate as we fall in and then decelerate as we fall away from these tiny asteroids, and that's a way to measure their mass. So essentially we can weigh them. We are a flyby mission, so we're not landing anything on these objects. There have been many other flyby missions. They are immensely productive. It's the only way we can get as many objects in one mission as we are getting. But despite that, we will be able to do surface geology with the images that we get over a range of angles. We get stereo. We will get maps of surface composition and structure. Like you can see here on the right, that's Pluto. We will, by measuring the mass and carefully measuring the shape, we'll get the density of the object, and that will tell us a lot about the interior. And we'll search for satellites and rings, which tells us a lot about the collisional history and formation processes of these objects. So that's sort of, in the shortest possible way, a description of the kinds of science that we want to do. All right, and I'm going to circle back here to what I said right up top, which is that Lucy is people. There are more than 500, and I think that's a gross underestimate. It's probably closer to 1,000 that have worked on the design, building, and testing of Lucy. It's a spacecraft with the wings unfurled. It's about as tall as a 4-story building, weighs about as much as a small SUV. It has almost more than 2 miles of wiring in it. It's mostly wires and fuel. But, you can see this is a different group that includes some scientists, but this is a lot of the engineers and some of our financial people. And we have people working in just about every kind of thing you can imagine that you would use in any large venture. We have to have money, we have to have schedules, we have to have materials, they have to be tested and documented and so on. So for anybody that's interested in space, there's definitely room for you. And you just have to figure out what you love and then point yourself in that direction. Okay, I'm going to end with this. That's a photo I took shortly after launch, just a little bit less than a year ago. That loop you see is the contrail left from the launch. And I think we're going to turn it over to Tiffany now.
Thanks so much, Keith. I'm really excited to be here and take what Keith shared with you about the mission and talk to you a little bit about what resources we have, what tools we have available to you to help you take the content to your classroom or to your students or to your museum. I saw someone was on here as potentially as an informal educator as well. So if you're at an informal site like a planetarium, and we'll definitely, I've seen some more questions in the chat, and we'll definitely get to those at the end. But before we get to some questions, and before I start talking about all of the resources that we have, I noticed the vast majority of people who were coming in and were able to answer the polls or respond to the polls were teaching in the K-12 arena. And I'm curious, for those of you who are using, teaching science and potentially either using NGSS standards or something similar. I know here I'm in Colorado and our state standards are basically copy and paste of the NGSS. But if you're using those and if you're teaching in any way with phenomena, I'd love to hear what kind of phenomena you just saw, what kind of parts of the Lucy mission stuck out at you, stuck out for you as, that I could offer that idea or that concept or that observation to my students and it could be an entry point for us to explore and engage and learn more and figure out more. So if you're using phenomena, I'm wondering, what kind of phenomena do you see with the Lucy mission, just from what Keith was talking about? Yeah, so rings, and go ahead if you've got something, drop it into the chat. Asteroids with rings, yeah, that's kind of interesting. And what Keith talked about was that we're not really sure exactly what that process is. The slingshot with gravity works for forces. Yeah, so whether you're looking at phenomena or just want some great examples of some of the content that you're looking for, using a thermometer to measure the surface temperature at night versus day, and this can tell you what the surface is made of and its composition. Yeah. And the naming, it kind of connects it to some of the other sciences as well as the social studies and things like that. The story of how Lucy was named, I like that too. So when I was thinking about how would I, if I wanted to pick a driving question or a phenomenon that could really drive engagement for the students, some of the ones that stuck out to me were this idea that there are, let's see if I can get this back up. There we go. That we've got these asteroids in these very specific places out here. How are they being held in place? What's going on there? How did they get there? And why are they not in a big circle like in the asteroid belt? If I wanted to get my students thinking, what doesn't make sense here? What is not quite adding up? There's one phenomenon. What's going on? How did those asteroids get there? Maybe the students have heard about Lagrange points. Maybe they haven't. Maybe that's part of the exploration. Another one I thought of was, we've got several tools or instruments on the spacecraft, and I think somebody brought it up with the thermometer to measure the surface temperatures. Lucy is not going to land on a single asteroid. So how, from a distance, are we going to learn what these asteroids are made of? Well, how is this going to tell us about the history of our solar system? So maybe a deep dive into the tools that are being used on Lucy. And then somebody else brought it up with that slingshot idea. But wait, doesn't gravity pull things towards the Earth? And wait, this is a gravity assist pushing it out further into space. And for some students, that might take a little bit of time, a little bit of need to think and really assess what's going on there with the push and the pull and different forces. So there's some different ways that you can engage your students right in the very content that you need to cover, but using Lucy as an option. I have gone through and just pulled up some of the space systems. So if you're using NGSS, for the lower grades in 5th grade, you're going to have, a little bit of gravitational forces, an argument that gravitational force exerted on Earth by Earth on objects is directed down. For 3rd grade, it's a little bit about balanced and unbalanced forces. So, you may or may not be able to, with a 3rd grade group, I'm not sure that I would just give them this idea that gravity is pushing is speeding up the spacecraft. But if they're already studying balanced and unbalanced forces, then Lucy may be a really nice example. For the older students, as we go into middle school, they're going to, the space systems standards are right in line with what's going on with Lucy here. The model of lunar phases and eclipses of the sun and moons is actually is directly related to the way that the most recent asteroid for the Lucy mission was found, and that was with those occultations. So instead of the moon blocking out the sun, an asteroid is blocking out a star for a brief amount of time, but very much like an eclipse. So there's some, ways to extend the learning. Use a model to describe the role of gravity in the motions with galaxies and the solar system. So there's those Lagrange points again. And then going on. Let's see. And really, I think the main message here is that if you look towards forces and interactions and the solar system standards, you're going to find connections to Lucy. So given that, beyond what you just learned from Keith, what are some of the resources that might help you bring this into your classroom or bring it to your students wherever they are? And we do have a resource page that I'm not going to send you to just this minute, but I want to point out everything that's on this resource page, and it's all specific to Lucy. And when you go on there, you'll find videos and among other things. And one of the videos that you'll find is, if you were on before Barbie started talking this evening, we were showing Lucy's journey, 6 episodes about the Lucy mission. It is an Intrepid Explorer cartoon, but it's the science is all there. So it's a great short video for, you know, students of all ages. I've seen adults love it. I've worked with, you know, Girl Scout troops of all ages that just, it kind of gives a really nice brief introduction. You could use it as something to, you know, get their attention. It's 6 episodes. Each episode is only a couple minutes long, or you can just run them all together like we did at the beginning of this session. And tomorrow we have a brand new episode coming out all about the Earth Gravity Assist. And for your viewing pleasure, I have been able to get a sneak peek of this video, and Barbie's going to bring it up so we can play it this evening. So you are the first audience to see our 7th episode. I promise if you haven't seen the first 6, it's not going to ruin, there's no spoilers here. This is just about the Earth Gravity Assist. So I'm going to go ahead and play it and let you enjoy.
It's been a year since our intrepid explorer Lucy launched on her 12-year-long journey to the Trojan asteroids. Oh hey, you're coming back our way. You'll need a little bit of help from Earth to boost you all the way to your Trojan asteroid targets. This is an Earth Gravity Assist, or EGA. There we are. Planet Earth. Okay, Lucy. So this is the first of 2 EGAs to get out to the Trojan asteroids, with another to allow you to finish your tour. Each pass by Earth gives you that extra kick to get you all the way out deeper to space and steers you on the right track to your asteroid rendezvous. Whoa, wait just a second, Lucy. The team here on Earth is doing some calculations to make sure you don't knock into any satellites or debris as you make your pass over us. Make sure to grab some images of Earth and the Moon on your way in. It'll also help us test your cameras and get you calibrated. The NASA Collision Assessment Risk Analysis team might have you do some small engine burn maneuvers to avoid crashing into anything. Some parts of the world, like here in Western Australia, will see you soaring over us like a star in the night sky. Others in the Western United States will be able to see you with binoculars. It was great seeing you pass through, Lucy. We'll see you again in December 2024 for your 2nd Earth Gravity Assist that'll boost you out even further to get you your first look at the Trojan asteroids.
So this will be available. So all the first 6 episodes are available. You can use that link that will be in the slide deck once it's shared with you. But then the 7th episode should be uploaded hopefully by tomorrow, but it will definitely be available. You'll be able to look for it with social media or something like that. So if you wanted to share it with your class tomorrow, you could probably access it just by getting into the resource list and then looking on YouTube where it takes you to YouTube, because that resource list really just pulls in all of the resources that are available out there and gives you access to them. One of the other series that we have available is Exploring the Solar System with Lucy. So it takes advantage of the cartoon character, but also brings in real people from the Lucy team. There's 5 episodes. They're standalone. So you could pick the one videos that work for you in your classroom, depending on what you're trying to focus on. So we've got Exploring the Solar System, and that's with our project. That's with Hal Levison. We've got Lagrange points, so really focusing on that gravity interactions and how those Trojan asteroids got stuck there in the first place. Planning a spacecraft launch. The one that might work if you're really highlighting the Earth gravity assist is driving a spacecraft. So that's the one, that's the picture here. And then like Keith has mentioned, there is a job for anyone with NASA or on a NASA mission. And so working on a NASA mission really highlights a wide variety of people on our team, just to kind of give the students an idea of what it takes to work on a NASA mission, or what interests that they might have that could take them there. So I think that's a really nice resource as well. Additional outreach resources or classroom resources that you might find on this resource list include additional videos and animations. The ones that I've highlighted have been more cartoony, but there's a lot of explainer videos on there as well, including some great ones about how the different instruments on Lucy will gather data and how that data will be used. So there's some good videos and animations. There's also posters, graphics. You can even download phone and computer wallpapers. We've got some different crafts and activities. If you wanted to build a paper Lucy or something like that, there's instructions on how to do that. And then my personal favorite is the Lucy coloring book and activity pages. You can download just the activity pages one at a time, or the full coloring book, which both are really fun and educational. We went with activity pages just instead of the coloring book, or just a coloring book. And I'm going to apologize. I tried to hide anything that might make them bark, but here we go. So that's our resource pages. Aside from that big resource page, which we will share through this slide deck, I also want to point out some other great places for gathering content, images for your students. The Lucy Mission social media accounts, we've been posting at least one item per day leading up to the Earth Gravity Assist. And you can find us on Twitter, Facebook, and Instagram. We'll also have a couple calls to action where you can get your students or clubs and groups involved and posting as well. So I encourage you to look at our social media. In addition to the Lucy accounts, Lucy information also is posted on NASA's solar system accounts, which are also on Twitter, Facebook, and Instagram. So if you're on any of those 3 platforms, you can follow the Lucy account, or you can follow the NASA solar system accounts. The solar system account, of course, is going to include a lot more content, including Lucy. And the last place I want to point out as a resource that's specific to Lucy is 2 websites. And actually, with the lucy.swri.edu, this is the Lucy mission site that is run by the by Southwest Research Institute. And the last thing I wanted to show you, and I do want to kind of keep it quick, but Barbie, I'm going to have you let me share that video, and I'll probably speed it up a little bit. If you have not been on this website, which is Eyes on the Solar System, this is from NASA's JPL, and it is a fantastic resource. I made this into a video so that I wouldn't have to run it live, because that would slow down our our bandwidth. But basically, you can go anywhere in the solar system, including any of the spacecrafts in this list. So you could just click on the list of spacecrafts. I clicked on Lucy. It'll take me directly to Lucy in real time. You'll notice that there's a live, it says that it's live in green. So that means that you're seeing Lucy in real time as the spacecraft is right now. You can move the spacecraft around and resituate it. So you can click on the left to see where is the spacecraft from the view of the sun. And that's just in the menu on the left under view options. Then you can also go back and navigate back to where Lucy is. So just click on near Lucy and you get back to Lucy. And what I really like about this is that I can speed up the rate that this is going, and I can watch the Earth gravity assist as it's happening. So this is something that you could show the students, whether or not you're going to be able to see Lucy from Earth. You can still observe and get a feel for what is happening out there in space. So you'll notice that I'm adjusting it so that now I can see the Earth. The sun is shining on the beautiful solar panels, reflecting and making them really shiny and beautiful. And in the distance, there's Earth. And if I want to, I can speed up the time to, now I'm at 30 seconds per second, 40 seconds per second. And pretty soon, if I get it fast enough, I'll start to see the Earth coming in closer as Lucy approaches the Earth for Earth gravity assist. If you're trying this at home, and I really encourage you to, this is such a fun website for you and your students. You can just explore till your heart's content, but you have to practice moving things around a little bit. So don't go too fast until you're feeling confident. And you'll notice here is I slow myself down a little bit when I know I'm getting closer to Earth, because I don't want to go zooming by too fast, and resituate so I can still see the Earth in front of me. Now the Earth does look a little bit funny off there in the distance. Oh, it just twisted, so I'll have to readjust that. But the Earth looks a little funny, and what's happened is all of the orbiters around Earth are being shown in this version of Eyes on the Solar System. So I can go over to the menu under Lucy, and I can click the little box next to orbiters and turn those off. And now I can actually see the Earth and see it, feel the approach as we're getting closer. I'll slow things down a little bit, but basically what you can do here is you can tweak it just a little bit, until you just can follow all the way through. And this takes a little bit of time. I don't want to go into it too much because we're almost at the hour, but I just wanted to give you an idea of what you can do. You really can get all the way in. You can turn the orbiters back on and notice that as Lucy is going through the closest approach, the spacecraft is closer to the Earth than some of those orbiter orbits. And you can get a real good feel. You can see even as Lucy is approaching Earth, the spacecraft is going to have a beautiful view of Africa and may even be able to get some pictures of Ethiopia, where the original Lucy fossil was found. We're not sure that those pictures are going to turn out very well because they're probably going to be overexposed. So the Earth is going to be too bright. We're not expecting that amount of light where the instruments are supposed to work way out in Jupiter's Trojan asteroids. But it's still kind of fun to test that out and get calibrated. And at the same time, Lucy will be taking some pictures of the moon to calibrate the instruments as well. So I'm going to go ahead and stop this. And Barbie, if you can pull back up my slide deck. I just wanted to highlight that I really think it's a fun tool for you and your students to learn about Lucy or any other mission for that matter. last things I want to bring up, we do have a couple of calls to action on social media. You will be able to wave at Lucy. If you noticed, Lucy's solar panels were completely lit up all the way on that approach to Earth because the sun is directly behind Lucy. So if you go outside right now and wave at the sun, you will be waving at Lucy. So I'd love to see the Facebook or Twitter or Instagram just filled with people waving to Lucy, and use that hashtag. Take a picture of your students, take a picture of yourself, make a sign if you want to, but we're going to be pushing that for the rest of the week on social media. And then, of course, if you are in a place where you might be able to spot the spacecraft, love for you to share your experience with that on social media as well. I know that's a little bit trickier with the times and everything, but if you are able to get out there early in the morning on October 16th, and you're out there with binoculars or you're out there with a telescope, let us know. We'd love to know who else is out there with us looking up at the sky. So that's it. And